Hi, my name is David Srivastava, and today I'll be presenting my experiment 4, magnetic braking with Faraday. To get the understanding of the slab, it is important to understand some key formulas. One of them is the Biot-Savart law, which we went over in lab 2, which gives the magnetic field. The second one is that the EMF is equal to the negative change in the flux over change in time. This is Faraday's law combined with Lenz's law because of the negative sign. Then the third one is F equals ma. Basically, it encapsulates Newton's second and third laws, which also state that the sum of the forces has to be equal to zero. And the fourth is V equals I, our very common law when it comes to electricity and magnetism. To gain the purpose of this lab is to utilize and gain a deep understanding of Faraday's laws in real life and to gain an understanding of induced currents and voltage resulting from a magnetic flux. To set up this lab, you get an aluminum foil, fold the aluminum foil to make a tube, get a bar magnet, mark north using a magnetometer, and then drop it through the tube and measure the time that it takes to fall through the tube. You want to consider gravity and magnetic forces acting on the magnet. In this lab, I ran the experiment 5 times just to get a understanding of the average time it took for the magnet to fall. The average time was around 5.57 seconds based off of my 5 runs. Some questions that the lab has us considering is, why can't we use a Ferris tube? Because the tube will attract the magnet to it and there's way too strong of an attraction, so the magnet just won't fall. And what happens to the magnet? How does this compare to a magnet falling in free space without a tube? The magnet creates an attraction to the aluminum, but not strong enough to immediately attract each other. This attraction causes a magnetic force, causing the bar magnet to fall slower than it would otherwise. Now I'll go over some of the code snippets that are there. In step 1, we just set up the properties of the magnet, including the magnetic dipole moment. And then we also want to define like the Biot-Savart law, which calculates the magnetic field caused by the magnet. Then also the flux analytic, which is under part 3. Then in part 4, you'll see that this pretty much just sets up the graph over time. And then near the middle of it, we set up and calculate the flux using the various factors of the ring. This is the result of my code snippet. As we see, the time it took for it to fall, the magnet to fall, is 5.662 seconds, which is very close to my calculated result of 5.57. And there were a couple questions over here as well. The intensity of the coloring of the tube indicates the magnitude of current flowing through each ring. Red and blue indicate current flowing in opposite directions. We could see that red is the counterclockwise and blue is the clockwise direction. This is described through Lenz's law. What happens to the dynamics of the system when you flip the magnet around? The magnet will fall through with the directions of the current flipping, so it will fall more slowly. How does the total time and tube of your real world system compare to that of your computational system? How might the computational system be made more accurate? Pretty much. The greater the moment, the slower the fall. So the computational system pretty much calculates in a perfect situation how fast the magnet will fall. While in real time there could be some human errors, including like any additional starting velocity in case of me by accident pushing the magnet down. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? At the beginning and the end of the run, you can see that the gravitational force dominates the magnetic force, and throughout the middle, when the velocity is not changing, that's when the sum of the forces is equal to zero, meaning that the force of gravity and the force of the magnetic force created are the same. Some possible errors is incorrect measuring of the magnetic moment in lab 2 and any additional starting velocity that isn't 0 meters per second as covered earlier. And what if the resistivity of conductor reduced to as close to 0? Due to Ohm's law, the induced current in an aluminum tube will be greater, causing a greater magnetic force counteracting gravity force, causing the magnet to not fall. And what if holes or slots were cut into the tube? The induced current will be less as the holes will disrupt the current, causing the magnet to fall faster. Thank you so much.